Amphenol Broadband Solutions is a global leader in the manufacture and engineering of interconnect RF and optical products, as well as solutions across the entire spectrum of broadband network topologies, including wireless, copper, fiber, and satellite. Headquartered in Wallingford, Connecticut, ABS is a division of Amphenol Corporation, a Fortune 500 company with a nearly 100-year history as a leading diversified interconnect manufacturer. While Amphenol Corporation supports nearly every major global industry, Amphenol Broadband Solutions supports advanced communication networks by providing critical technology to over 200 service providers in 40 countries. With strategic manufacturing and distribution locations around the world, including facilities in North America, Europe, Asia, and Latin America, Amphenol Broadband Solutions offers hardware, design, and inventory management solutions, along with multi-level training and deployment programs. Our worldwide footprint allows the flexibility to support customers in today's constantly changing environment. Recently, the broadband industry has dealt with trade wars, political instability, and a global health crisis, while providing essential communication services for schools, distance learning, hospitals, essential services, and the explosion of a workforce telecommuting from home. Amphenol Broadband Solutions' footprint gives us the agility to adapt and ensures that we continue to innovate and supply the world's service providers, as well as their end users. At ABS, we remain laser-focused on continuing new product development, coupled with strategic acquisitions, to offer complete end-to-end innovative solutions that cover inside plant through to demarcation, whether using RF, optical, or wireless technology.
Hi, my name is Owen Barthelmess. I am the Director of Engineering for the RF division of Amphenol. I'm part of the Amphenol Broadband Solutions group, and my focus is interconnect technologies that complement the suite of products that Broadband Solutions offers. Today I'm going to be focused on introducing a new product that we're very excited about. This new product is called the NDX connector, and it is designed and intended for this broadband market. So the genesis of NDX, where did NDX come from? Well, it all started with an evolution first of the CATV systems themselves. As you look over the years, the CATV systems have evolved, starting with DOCSIS 1.0. Of course, there were systems even before that, but DOCSIS 1.0, 1.1, 2.0, 3.0, 3.1, which is what we see as most of the deployments out there right now. And then, of course, we have DOCSIS 4.0, which is forthcoming. Through all these years, we've seen a lot of evolution in the connector systems that have been used in these various systems. But we haven't seen a lot of evolution in the connector that's used specifically for RF in this market. So, it's going all the way back to the 1950s. We see there's a Type F connector that was introduced. Composite video was introduced. And there's been a lot of improvements to many of the interconnect solutions over the years. A composite going to S-video, going to component video, to HDMI. We have various other interfaces that have evolved, but we haven't seen any evolution of the RF connector itself, the Type F connector. Amphenol itself has a lot of history with high-performance push-on connectors. And so as we came to this new challenge of how can we design the best connector for the broadband market, broadband networks, we looked at what we know already, what works well, what we've used in the past, and we built on that with some new technologies. We've seen now that Type F has kind of reached its useful limit with DOCSIS 4.0 being introduced. As 4.0 is introduced and we're pushing frequencies from the current, in general, 1 gigahertz type systems that are out there in the networks. Now we're pushing to 1.2. We're seeing a new push all the way to 1.8. And the DOCSIS 4.0 spec is being written around a 3 gigahertz maximum, which is a pretty significant jump from the 1 gigahertz systems, which work well with Type F connectors today. So we see this as a new challenge moving into the future. We were inspired as we developed this new connector by best practices, not only from connectors that we produce ourselves, but across all of Amphenol and all the technologies that we bring to multiple markets, and looking at what were the best performance, ergonomics, and ability to adapt to high volume in the future as these new high-performance systems are deployed. So with NDX, we're combining some new patent-pending features that satisfy tomorrow's requirements that layer on top of the best practices that we know for interconnect across multiple markets. So NDX, what does that stand for? NDX stands for Next Generation Dual Shield Extended Spectrum. So that's really the key of the interface. And what we did is we deployed this product is we really set a mission statement to look at 5 key areas, as you see here in the presentation. One key initiative was to provide an intuitive user experience suitable for consumer level usage. This is really a key for the interface and a key building block. We know that this connector gets deployed out there in the field and consumers use this very much like they use an HDMI connector, an Ethernet connector. These are connectors that they've come accustomed to and consumers use on a daily basis and they're familiar with. So we wanted to have a similar user experience than those types of interconnect. We also wanted to enable bandwidth expansion, not only for this next generation of DOCSIS 4.0 that's being released, but also for future systems, future protocols. So we wanted to develop a lot more headroom into the interface as we launch this. We want to deliver compatibility with the existing tooling infrastructure. So look, we know there's a lot of tools out there. There's a lot of technicians that know the current product well. They have all the tooling needed to put this, to build the networks and keep them running well. We wanted to really be compatible with that and not change that too much. We wanted to reduce the total cost of ownership across the value chain, especially reduce truck rolls. The current climate, more than ever, self-installs are critical, and we need a product where this can be sent to any customer. They can pick it up, and it's very intuitive. They can install this themselves, and it doesn't introduce any new issues that may have to be diagnosed by a technician in the field. And ultimately, we also need to achieve high RF ingress protection against current and future wireless bands. As you know, in the current systems today, there's a lot of potential interference between LTE and the broadband networks. But as we expand into new bands, as we expand up into the 1 gigahertz, 2 gigahertz, 3 gigahertz bands, we come across a lot of other potential interference that we need to protect against. So high RF ingress protection was also a critical component. So let's get into what this interface is a little bit. So as we see pictured here, this is a typical configuration for this interface. We see what we call the plug side here, attaches most commonly to cable. And then we see the jack side, which would be most likely installed inside of premises equipment, say a set-top box or a cable modem. And really key feature of this interface is it's a push-on, snap-on interface. It's not a threaded interface. The plug itself is a fairly simple construction. It's got a pinned interface, and then the jack is a little bit more complex in terms of components and design and really some key features that enable its high performance. But we really focused on best practices, as I said earlier, in manufacturability so that we could scale the manufacturing of this to very high volumes as this starts to be deployed into DOCSIS 4.0 systems. So we used heat metal stamping and forming, injection molding, automated assembly, processes we know well from other industries and know that adapt well to very, very high volume production at a very attractive price point. This is how the product looks. As you see on the cable side, really straightforward, quite simple design. We really attempted to keep it that way. As you see, one key feature is the compression crimp. So that essentially this back end of the connector that attaches to cable is identical to all the Type Fs that are out there today. Can be adapted to any compression crimp style design that exists today. And then all we've changed is the front side of it, which is the new NDX interface. As you can see here, it's a pinned interface. It's a round machined interface, quite a simple construction, not a lot of complexity, but a lot of key features that enable the technology. Then on the jack side inside the equipment, we have pictured a right angle connector down to a printed circuit board. It can be a vertical connector, can be edge launch, can be all the different normal configurations we're used to in RF type products. But this is a sort of a standard configuration that we envision being high volume. So you can see it's very similar to, say, like an HDMI or a USB type construction, with the manufacturing method, which really enables this to be a low-cost, high-performance product that can be scaled to high volume. This is how the product looks integrated into a cable modem. And really, this is really the key to the product is when you take this product and you use it and you actually just engage the connector, it's a very simple thing, but it has a very user-friendly, audible, tactile feedback when you engage the connector and mate it. So you hear it, you feel it, you know that it's fully mated. It's not a high force to mate it, it's just right. You click it in place, it feels solid, you can hang the modem by the connector and it does not come apart. You can shake the modem, it does not come apart. It's a very solid connection, but also if you demate it, you just need to give it a little bit more of a pull, disengages. Very simple to use. We think that the consumer will really embrace this new technology. It can also be adapted to conventional wall plate home installations, should that be a need in the future. On the outside of the wall plate, of course, would be an NDX connector. On the inside of the wall plate is could be a type F connector, or it could be NDX. So it could adapt to existing infrastructure, or it could be a complete ground up home wiring or commercial wiring application where NDX is used throughout the entire network. It really is flexible in that way. So let's talk a little bit about what makes the interface special, what is different about this product. As I said before, we named this product a dual shield product, and that's very important. If you look at the interface here, we actually have what we call a primary RF ground and a secondary RF ground. The signal line itself is shown here in the center, pretty straightforward, pin and socket joint. As I said, the interface itself is pinned, which makes it very robust, allows us to put low conductivity or high conductivity, low contact resistance plating on there for long product life and have very consistent length and diameter versus a connector that may use the cable as the interface. But as we move to the ground is really the key of the new technology. You see that we first had this primary ground, and this is a spring contact system. And the ground makes contact to the jack, makes contact to the inside of the plug, and it's a very robust electrical connection. So this is the primary electrical connection point. It's located very close to the interface itself, which enables it to be a high frequency connector. But then as we move outward, you see there's a secondary RF ground, and that is really the key to the interface. This secondary ground embraces some technology that we developed in other products or have seen in other products, where what we're able to do is mute any RF ingress by strategically placing a ground in the right location. So in this product here, what we've configured is a ground right on the outside of this mating connector, and through a lot of analysis and testing, we found that that actually creates really great RF ingress protection by creating the second contact joint here. We also use this second contact joint as the mechanical joint itself. So you can see there's a detent in the outside of this plug connector. As the plug connector gets pushed in, it flexes out this flexible contact member and then snaps into place. That's what gives the audible, tactile feedback of the mating system, but at the same time, we're using that as an electrical contact joint. Now, one kind of secret of the interface is we put this mechanical joint on the outside of the connector versus on the inside of the connector like it is on some other connectors. That's really critical for this because this mechanical contact joint is a lot more aggressive from a mechanical perspective. It wears the plating more, it wears the metal more. We want to keep that away from the primary electrical joint. So we have a nice smooth contact joint for the electrical primary ground. That ensures that we have consistent performance over very high mating cycles. But then we move the mechanical electrical joint to the outside, so as this starts to wear over high mating cycles, we don't introduce any issues to the interface itself. We keep them on the outside of the connector. So it's really just a basic key feature that enables this technology in the NDX. Also from the interface itself, it's completely closed entry. You see we have some protruding dielectric on the inside of the interface. This is key. This protects these outer contact ground shield fingers, spring fingers, from ever being damaged, so it makes it much more robust. It's also a closed entry interface, so the pin is guided into the female socket So it makes it much more robust and positive mating. And the interface itself is also scoop proof, meaning as you mate this connector with the plug, if you come in at a very high off angle, very aggressive, doesn't matter how you try to mate this from the side, the interface is recessed in this jack body. And what that does is it forces the plug to be fully aligned before the connector mates. So a lot of subtle features we've integrated together to make this a very robust product. So let's compare a little bit to a product that we all know very well, which is Type F. Type F works well when it's properly tightened. The key to a Type F is it is a threaded interface. So as you thread this interface, you create a butt joint here. It's metal to metal at the face of the interface. And when that is fully sealed together, that creates a very good RF mate and prevents RF from leaking in or out. That's great. The problem is the Type F is not always tightened completely. This is a known problem in the industry. And when it's not tightened completely, then there can be issues with RF ingress and reduced performance. So that causes, technicians to have to go out and troubleshoot the issue because the consumer themselves are actually putting this together. And they don't really know this connector. They don't know connectors well, and they don't know that they have to tighten it completely and how critical that is. So what do we do with the NDX? We have this feature I explained earlier, which is the first shield and the second shield. It's a dual shield advantage. With a typical push-on type connector where you have a spring contact, you are inherently going to have some amount of leakage past these spring contacts. We just allow that to happen. We embrace it with this new technology. So that small amount of the RF that leaks past the first shield makes it around here and then encounters the second shield. So this second contact point placed on the outside of the connector, which is critical for this interface, now mutes that RF that can leak out, and therefore also the RF that could leak in and create an interference issue with the CATV network. So this is really, these two shields working together are what makes this a highly shielded product. And the beauty of this is it's not dependent on how well it's tightened. It's very tolerant to the position of this because they're sliding contact joints. And this is very obvious to the customer that this is fully mated because this snaps into place and gives them that audible tactile feedback. They snap it in place, they walk away. It just works. They don't have to think about it more. They don't have to torque it to any specific amount. It's just a good working solution. So here's a little comparison of Type F compared to NDX. As you see, they're about the same size. We did that intentionally. For one thing, we wanted to adapt it to the traditional compression crimp interfaces on the backside, and that drives a certain diameter. These are kind of fixed in place by the compression crimp technologies that have been proven and are out there in the industry today. So that's kind of a set diameter in the industry. It drives the pitch for a multi-port type application. So we set the interface to adapt well to that, be large enough so that it's still robust and fit well with that compression crimp back end. So you can see on both sides, the interface side by side is pretty close in size between the NDX and the Type F. The interface specifications, we've set these specifications, and we think these are, this is kind of what we're most excited about, how much we've achieved with the performance here. As you see, we've set the bar high. This is an 18 gigahertz connector. Here we are talking about DOCSIS 4.0 and 3 gigahertz bandwidth, and we're not stopping there. We know that we need a new connector. It needs to work for the system we're deploying today, DOCSIS 4.0, but it also needs to work for the systems beyond that. So we set a very high bar. We set an 18 gigahertz bar for this product. We also achieved very excellent RF leakage. We set the bar at what is very similar to what Type F is, about 100 dB of shielding protection, up to 1.8 gigahertz, which is primarily the current deployments that we're seeing for ESD DOCSIS 4.0 applications. And then as we move up in the frequency range, of course, it's more challenging to do RF ingress protection and RF shielding. It's just inherent, the physics behind RF, that's how it works. But as we look there, we have the specification of 90 dB up to 3 gigahertz and 80 dB up to 6 gigahertz. So as we move off into future networks, we still have very good ingress protection there. We have a 5 amp current handling capability. That's if there's power that's going to be run over this at all for power over coax. So it's capable with those technologies. And as we look at mechanical engagement forces, typical forces we see for engagement is about 3 pounds, disengagement about 4 pounds. And just to put that into perspective, if we compare that to what the HDMI spec is, which is a very well-known connector in the industry, we see that it is about 10 pounds max is the requirement. And you see we have about 3 pounds typical. So we're in a very good position there relative to how the other product works. And disengagement, we have 4 pounds typical. And you see that the range for HDMI is 2.2 min and 8 pounds max. So it falls right there in terms of disengagement force as a similar force to HDMI. So we're very excited about that as well. We have our mating durability set at 1,000 cycles. We think this gives excellent headroom for the product for typical applications. We've actually already tested the product at 5,000 cycles, has worked very well up to those cycles. So there's a lot of headroom beyond that too. It's a very robust product, but this is, I think, an excellent specification for the industry and the applications where it's used. Here's a typical return loss performance of this connector. So this is a full mated pair of RF connectors. And as you can see, the performance is excellent. As we look into the typical bands we're working on today, less than 2 gigahertz, it's better than 40 dB. If we look at up to 3 gigahertz, which is kind of the max, the DOCSIS 4.0, still better than 40 dB. So really good performance can be achieved with this interface. We're excited about that. But as you start to go up into higher frequencies, all the way up here to 7, 8 gigahertz, we're at 20 dB reflection. So really excellent performance even at those high frequencies. And taking that all the way up to 18 gigahertz, we're at about 13 dB up to 18 gigahertz, which is really excellent for digital protocols that need that headroom for the harmonics in the digital signal. RF leakage, another area, as I mentioned, we're very excited about that. This is actually achieved performance. This is actually a test of the actual interface. And you can see here up to 1.2, we are achieving 103 dB. And then up to 3 gigahertz, we're seeing about 100 dB, maybe 97 dB, all the way up to 3 gigahertz. So really excellent RF ingress protection all the way up to even 3 gigahertz. And very consistent too. There's not a lot of variability in this. Every time you made it, you get that same number. Where you don't have, where with a Type F connector, you can see a lot of variability in that depending on how much it is tightened. A little bit of a comparison of the specifications. Really, I think the key point here is, the NDX goes to 18 gigahertz. We're going to rate it like that from the beginning. The specs for Type F are really only up to 1. It can work to higher, but it's really only specified to 1 gigahertz right now. MCX has performance to 6, but it really doesn't have the leakage protection because it's a single shield connector, not a dual shield connector like NDX. So it doesn't work for RF ingress protection that is required by the industry. As you compare it to the RF performance to a Type F directly, you can see that the NDX connector is excellent performance. And what you see with the Type F connector is the Type F can be good, but most likely it's not good. And that's the biggest issue with Type F. There's so much variability in the performance. The connectors that are out there in the network right now, they may work to 2 gigahertz. They probably don't. And which ones do and which ones don't, it's very hard to differentiate that. With an NDX, it's guaranteed. This connector is designed to go to 18 and it performs extremely well up to 3 gigahertz. It's a guaranteed interface that's adaptable to the next gen technologies. And that's really its key feature. It's also for outdoor applications. So we have an outdoor version, which we're going to be promoting much more in the coming weeks and months. We're very excited about this version. It's very adaptable to the existing NDX that we're deploying and just converts that into a more robust interface for outdoor applications such as taps and other outdoor products. You can see the density is very similar to Type F, so the pitch can be kept at the same amount. So it's very much a drop-in with the existing package sizes, but more robust. And really a key to that robustness is the internal design for the outdoor applications. One key is that the interface itself uses a piston seal gasket. And what that piston seal does is ensures that we have a very good water ingress protection no matter how much this is mated. It's not dependent on how much the connector is torqued at all. Once that connector snaps in and is mated, the water protection is there. So it's pretty much guaranteed. So we're really excited about this. This is going to be the next part of the product that we're launching, and it really enables that same NDX interface and all the benefits, but in outdoor applications. So that is the end of my presentation. Thank you. Hope you're excited as much as we are about the NDX interface, and we're looking forward to over the next few months and years promoting this product and seeing it be successful in the market and solve the industry challenges of DOCSIS 4.0. Thank you.